Hello, my name is Milos, and this is my final project for the Harvard Summer School course, DGMD S17. If you want to know more about this course, I would first note that I also did a final project write-up. So if you want to know how to set this project up, how to install everything you need, and even open the project itself so you can try it on your end, I will include all of that in the project write-up. But as a general introduction, first of all, in order to actually achieve this in Unity, I needed to use Unity ML agents, and then ML agents needs TensorFlow, PyTorch, and for object detection I use C# OpenCV, and then I use some custom code as well. We'll get into all of these specifics later. So first of all, just to sort of explain what we're seeing here, here is a display breakdown. So first, screen one is just a focus view. That basically removes everything in front of the robot so that we can focus on the robot, hence the name. And then the second view is the third person view. This is looking from behind. Here's the third view. This is the first person view. And the cool thing about this is that it's exactly what the robot sees. And then here we have some statistics. These will come in handy later. But basically it's where the robot thinks the target is, how big the target is on the screen, and how the robot is orientated. So those are the key features. And then lastly, we have number 5 here. These are the annotations for the target. So you can see it says it right there. And then we have the screen space coordinates as well. So first talking about movement in Unity, specifically with the machine learning agents. It's pretty simple. We basically just have to get ML agents installed. And they already have a trained neural network, although we do have to make some adjustments. So you can see here they already have a 4-legged movement system. But it's not trained on vertically moving targets. So I had to train it a little more so that it can handle that as well. And then I also had to expose some of the values we're getting from the neural network so that we can later actually move the robot. And then lastly, I also had to adjust some dampening and motor torque to match what, for example, the motors we would use in real life. And then it needed some more training because I changed so many parameters. So first of all, for the object detection, as previously mentioned, I use OpenCV, but specifically a C# version of the library. And so here are the steps for detecting something in Unity. Basically, we just get a camera, and then the output of that camera we reroute into a render texture. So instead of going just to the screen, it goes to a render texture, and then the render texture we can just analyze as we would with any other frame stream. So first we sort of do some computation on the image so that we can make the target easier to distinguish. And then when we have a binary image of the target, we can find the contours, and that's basically our target. It's not shown here, but I also find the biggest target, so we're only focusing on the most obvious one. And then this is also interesting because we can distinguish between different shapes. So we could technically look for triangles or squares or any number of edges. And then the last thing is annotation. This is useful for both debugging and in general knowing what the robot is doing. And this is the final output. So another interesting and important aspect of object detection, in my opinion, is the data loss simulation. Because when we get images from real drones, which focus on delivering frames and they don't worry about data loss, we usually get these artifacts, and those are important because, as you can see, they can have various colors. So if we're specifically looking for a green target, this can actually interfere. And then also, besides just the data loss, we also want to simulate the imperfections of a camera, so distortion and lens dirt and stuff like that. So basically the way I did this is I just took my perfect image from Unity and then I overlaid this distortion and these imperfections to get a more realistic representation, and you'll see that later in the demonstration. Here's a list of all the various things I also simulated. So then the next step is, after we can detect the target, we want to stabilize the camera because this will help us in navigation. In my case, this is how the target is estimated, by using the camera. So it's pretty simple. We basically just want to stabilize on all 3 axes. So to stabilize along the X and Y, we just use the screen space position. So if it's too left, we rotate. If it's too far up, we rotate the camera, and so on. And then for the Z axis, we actually have the gyroscope. So we can just use that data and if it passes a certain threshold, we can rotate it to adjust. The only note here again is that we have to sort of refrain from using unrealistically strong motors, because it's possible in a simulation but wouldn't be realistic in when actually making a robot. And so then the interesting part is setting the destination. Basically, all I do here is I estimate the distance by looking at the screen size, and the robot already knows how big a cube like this would be up close, for example 1 unit away, so it can estimate the distance. And then the other factor there is sort of as a proximity sensor would be in a real robot, we have a raycast here which prevents the destination from going into walls. And so speaking of walls, aside from the destination, we also want to prevent the robot from getting stuck on walls. So I have these, again, proximity sensors. Specifically in Unity, these are called raycasts, where if the robot gets too close, the destination moves to the other side, and that way the robot knows that it should also move to that side. And just going back to the previous slide, one thing I forgot to point out is that this red sphere represents the robot's internal notion of where the target is, and the green cube is the actual target. So you can see here it's moved to the side because it wants to get away from the wall. And then lastly, I would like to give additional credit to Unity for making the ML agents free so that I could use the neural network that they trained. And also Aldo Biondi for providing me with the robot design, which again is the interesting part here, because this robot can actually be 3D printed and tested in real circumstances, which I think would be neat. So now we're going to go into the practical demonstration so you can see the robot in action. Aside from that, thank you very much for your attention, and I would once again note that you can reference the project write-up for more information. Thank you. All right, so welcome to the simulation now. First, we're going to look at the simpler simulation, which is in this clear plane, and this is basically the perfect scenario for this robot. So this is about as well as we can expect it to perform. So let's see how it behaves. Similarly to the more complex scene we're going to see later, it detects the target instantly and it keeps centered pretty well because, again, it is the perfect case scenario. You can see the light turning yellow as it's searching, and basic navigation isn't particularly difficult, although it does have a preferred side, it seems, which might have to do with the original neural network. And just letting it play here for a bit, you can see that there are no issues. So we can start to test it a little bit. So in this case, I start spawning objects to make it more difficult. And we even have explosions because this is a simulation. We can do whatever we want. But the good thing here you can see is that it's not deterred. So the idea is that even in the real world, if it had trouble, like animals or people, for example, it would still be able to navigate. And you can see here the camera flashing green and yellow. This basically means that the robot is having a little bit of trouble locking on. But it actually manages to lock on because it sort of tries to walk towards the target even though it's not 100% sure it's there. So you can see it's relatively reliable. So looking at the behavior here, we can see that it searches for a second before it finds the first target. It then finds the second target and it uses collision avoidance to go around that beanbag chair right there. And now again with the wall. Then when it finds the last target here, it moves, or rather it searches for the next target, again uses collision avoidance to get around the second beanbag, and same with the door frame here. And this way it can basically go from target to target. Now we can see in this specific case, the actual destination, or rather the internal destination is sort of blocking the view, but it does serve nicely to still demonstrate where the robot thinks it should go. And here it sort of struggles to decide which one is closer. But then when it does figure it out, it goes towards the bigger one. And when it finds the last one, it just sort of sits there and turns around infinitely until it finds something, but there's nothing to find. So finally, that covers pretty much all of it. I just wanted to thank you again for your attention and remind you that you can also read the write-up for more information. Thanks a lot.